The first law of thermodynamics means that the total quantity of energy in a closed system is conserved. That's a conservation principle. But the second law entails that the quality of this energy changes, so that free energy, or what's sometimes called exergy, is degraded into bound energy, okay? Energy that can't be used, right? This is a variational principle. So you've got a conservation principle and a variation principle. So when energy becomes bound energy, then no energy can be extracted and no work can be done unless it's coupled with a system, another system that introduces a difference. The asymmetric flow towards bound energy means that, in contrast with Newtonian mechanics, all natural processes are irreversible. Now, thermodynamics is often confused with statistical mechanics, and that's because statistical mechanics gives an explanation of the thermodynamic observation of increasing exhaustion of free energy, and it explains this in terms of increasing randomness or disorder. So if you read the Hemo paper the Schenker paper that I suggested, then you'll recognize this part. So Hemo and Schenker, this is actually from their book, but Hemo and Schenker argue that we should recognize that what's called the second law of thermodynamics actually consists of two time-directed laws. So one is the law of approach to equilibrium, and the other is the second law. So the law of approach to equilibrium describes the tendency of systems to approach equilibrium. So, for example, if we had a high-speed camera shots of a glass of water after a perturbation, so if we shake a glass of water and then we have high-speed camera shots of it, we should have a sequence of shots, and we should be able to organize those shots in the right order because we know that it goes towards equilibrium, right? So it's describing a sequence that's closer and closer to equilibrium. The second law describes another irreversible time-directed process. And this is the exhaustion of energy, so the inevitability of waste, or the impossibility of converting all energy to mechanical work. So here, the series are ordered according to increasing entropy, or decreasing exploitability of energy for mechanical work. It's important that those can be separated, and they're often confused. So both of these time-directed laws are empirical generalizations that are robust across a range of variations and scales of analysis, but they're contingent rather than a priori, and they're violated outside of their appropriate domain of application. So, for example, classical thermodynamics takes equilibrium to be a stable state from which a system doesn't deviate after it has been reached. So if we change the external constraints on the system, so for example, we have a gas and we remove the partition, then it will evolve to a new equilibrium state. And that the entropy of that new equilibrium state has to be equal to or higher than the previous state, right? But in classical theory, the system is always at equilibrium or lawfully approaching it. But if we take precise measurements of systems, actually there's small fluctuations away from equilibrium. And neither the law of approach to equilibrium nor the second law allow for any such deviations. And it's only by appealing to mechanics that the fluctuations can be accounted for. The problem is in mechanics, there's no asymmetry of time. There's just reversibility. So Boltzmann attempted, first of all, to provide a deterministic mechanical explanation of the law of approach to equilibrium. But there was various counter-arguments which led him to revise his claim. So he then formulated the statistical mechanical approach, which is probabilistic, basically. So instead of having an absolute kind of law, deterministic law that will take you to equilibrium, instead you have a high statistical probability that displays a law-like regularity. Okay, so the probability of approach to equilibrium is so high that you get approach to equilibrium, the idea. So basically, he's redescribing the time-directed laws in terms of statistical probabilities. So basically, this redescription allows you to, instead of taking it, basically, after the redescription, we can describe the unexploitability of bound energy in terms of the degree of mechanical control that you have over the system. Okay, so even if you have these very small fluctuations away from equilibrium, they'll be so unpredictable and random and so fast that we wouldn't be able to harness them for work, right? So effectively, the thermodynamic principles hold on the probabilistic kind of account. But this kind of recognition gives rise to another problem, which is known as Maxwell's demon. So if there was an entity that was small enough, fast enough, and intelligent enough to control the movement of microscale particles, then it could defeat this statistical tendency and effectively constitute a perpetual motion machine, flouting the laws of thermodynamics. So not only is this a sticking point for statistical mechanics, but also more fundamentally, the explanation of the two time asymmetric thermodynamic arrows of time by means of the time reversal invariant laws of classical mechanics demands an account of how the irreversibility of thermodynamic systems arises from the mechanistic symmetry, right? Because the laws of mechanics they nowhere tell us that we're going to have any kind of irreversible transitions. The central plank of thermodynamics that is the distinction between microstate and macrostate. So in classical mechanics, the evolution of a dynamic system can be plotted in state space, where the actual physical state of a system at any given time is its microstate, represented by a point in state space. Now, as Schenker points out in that article, which you hopefully read, this isn't a part-whole or small-big relationship, right? So a microstate is a complete description of an actually existing state of affairs. So the state of the universe at any time, at any point in time, according to this theory, will be a microstate, right? So it's not big, small.